Mhm.
Okay, so since it's been so much since the last session, I'm just going to give a quick recap of what we have done about Cartan decompositions. So remember that Cartan decompositions come from between the interaction of real structures on a complex semi-simple algebra and compact real structures that commute with our original structure. So remember that if we had a complex semi-simple algebra G, and we take an arbitrary real form of G real structure. Then we can create a Cartan involution for the real structure induced, for the real form induced by sigma by taking a compact real form that is compatible with sigma. So take a compact real structure such that lambda and sigma commute. And then we simply consider this composition, sigma tau, which we call theta. And this is clearly an involution of the Lie algebra G. Such that G, the real structure, the real form associated with sigma is preserved by theta. So say G0 is the real form. Then we have a restriction of theta from G0 to D0. So this is now an involution of real semi-simple Lie algebras. And we could consider the eigenspace decomposition of theta for G0, which gave us G0 equals K plus P, where K is the eigenspace of 1 and P is the eigenspace of -1. And then we also knew that this is a set to gradation in the sense that K is a subalgebra that normalizes P and the bracket of P with itself falls into K. So apart from this, we not only have this real form G0, we also have the real form associated with tau, the compact real form. So if U is equal to G tau, then we could also consider the restriction of theta to U. Again, theta preserves this other real form. And we also have an eigenspace decomposition. It's something of the sort. U equals U plus U minus, and this is precisely K plus I. So the real form G0 and the compact real form U differ by multiplication by I in the eigenspace of -1. Okay, so this was something that we already saw. Remember that the fact that theta is a Cartan involution comes from tau being compact, and recall that theta being a Cartan involution meant that the killing form is negative definite on K and positive definite on P. And we have already proved that given a real semi-simple Lie algebra, Cartan involutions on the real semi-simple Lie algebra are unique up to conjugation. But we are still left to see that when we are given a real semi-simple Lie algebra, then such an involution exists. But in reality, this is more or less what we have already done here. But simply for the sake of clarity, I'm going to write it. So theorem. Let B0 the a real semi-simple algebra. Then G0 admits a Cartan inversion. And the proof is pretty much direct. The only thing that we need to do is to realize G0 as the real form of its complexification and apply the argument given here. So take G to be the complexification of G0, and then G is associated to the G0, sorry, is associated to the real structure, which is simply conjugation. So let's say sigma from G maps x plus R1. So that zero is precisely the fixed point set at sigma. Okay. Now, simply choose a compact real form that commutes with sigma. We know that this exists by a result in chapter 3. Compact real structure. From G to G, such that sigma equals to sigma, and then simply take the composition of sigma and tau, and again this restricts to G0 and induces a Cartan involution. So theta is the decided. So we know that if we are given a real semi-simple algebra, then it always must admit a Cartan involution, and it's unique up to elements in the inner automorphism group of the Lie algebra G0. So now that we've seen these preliminary results, let's start by taking the Lie algebra SLNC. We will take all the real forms that we already know, and we will see which are the Cartan decompositions for those real forms. So, okay. Sample. SLNC, and we will compute the Cartan decompositions for all of these, all of its real forms. Okay. So the first example is going to be simply the compact real form, SUN. In this case, it's almost trivial. Simply we have G0 to SUN. Then the associated involution we saw in chapter 3, that it's simply the identity map of SLNC. So when we restrict the identity map to G0, it's also the identity map. And so the Cartan decomposition is going to be K to be equal to the whole of UN, and P is going to be the zero vector space. For the split case, let's take S on an R. The zero to be equal to S on an R. Then in this case, the associated involution is the wild involution, which in the case of S on C, we denote it by omega, and it takes any matrix X to minus the transpose of X. So the eigenspace of 1 is simply going to be the set of skew-symmetric matrices, while the eigenspace of -1 is simply the set of traceless symmetric matrices. So K is going to be the set. Which is supposed to be such that X prime is X, and this is simply the orthogonal algebra. And P is now the set of elements of the S in R, which coincide with this transfer. Okay. So for the, now if we take M to be even, then we can also consider the special linear Lie algebra over the quaternions. So this will be D0 to be SL and H, in the case that M is equal to M, which, if you remember, the involution was given by taking a matrix X and taking the conjugation by the following matrix Sm as an X transpose Sm minus 1, where Sm essentially represents the multiplication by J. 0 minus the identity is 0. So in order to determine the eigenspaces for this map, what one would do is to write a complex matrix in SLMH. So we know that a quaternionic matrix is represented as an n by n complex matrix in the following form. I always mess up this computation, so that this has happened. So a matrix is in SLMH. We can only if X is of the following form: AB minus conjugate of B and conjugate of X, where A and B are n by n complex matrices. So essentially, this represents the part in the 1I part, and B represents the part in the JK part of the quaternions. So if you go through the computations, it's not difficult to show that theta X is minus the conjugate transpose of A, transpose of B, minus the conjugate transpose of B, and minus A transpose. And this is precisely minus the conjugate transpose of X. So I don't know if you want to go through this calculation, but it's simply doing the necessary matrix computations. But
no, it's fine.
So I think I'm going to skip that. The computations are part of it in the notes anyway. So at any rate, just as in the split case, but for the quaternionic matrices, K is going to be the set of skew self-adjoint matrices, where P is going to be the set of self-adjoint matrices. So K is set of all X such that the conjugate transpose of x is equal to minus x, is precisely SPN, and P is the set of elements with S elements that are symmetric. Lastly, we also had SUPQ, where P and Q are non-negative integers. Fourth, we have G0 to be SUPQ. In this case, the involution theta was conjugated by IPQ, where IPQ is the standard metric of sigma plus PQ. So IPQ is the identity matrix, but having the first P elements to be -1, and the last Q elements to be 0. So there are 3 elements, and here are 3 elements. So if we take a matrix here, then we can write it as in the following fashion. It must be of the form A, B, B conjugate transpose. Now again, you simply do the conjugation by IPQ, and the result is going to be theta equals A minus B, B conjugate transpose. Now, if you simply equate x to theta x, what you get is that the eigenspace of 1 is going to be the set of block diagonal matrices of the form x1, such that x is in UP, y is in UQ, and the trace of this whole matrix is 0. The trace of x trace of y 0. And P is represented by the set of matrices of the form 0 set conjugate transpose set 0, where set is any P times Q matrix. Yeah. So really the hard work for finding these Cartan decompositions was done a long time ago in chapter 3. And this is just doing the direct computations in order to get the explicit expressions that consist of. So a second example is going to be taking the Cartan decomposition of a complex semisimple Lie algebra when we see it as a real semisimple Lie algebra. And it's going to be related with the compact real forms. So suppose now that let's give me a complex semisimple Lie algebra. And we consider the real semisimple Lie algebra, which is simply the realification of G. So we forget the complex multiplication. Okay. So I don't know. So from chapter 2, we know that we can recover this real semisimple Lie algebra as a real form of G times G. So it was done in the following way. So GR is the real form of G plus G by the following anti-involution. should be sigma G plus G to itself. So X y to tau y tau X, where tau is any real form for choosing. It doesn't need to be compact. So tau should be a compact real form. So tau is a real structure. Now, we need to find an involution that commutes, an anti-involution that commutes with this real structure. And the easiest way to do this is to assume that the tau that we're picking here is compact, and to take simply the direct sum of tau with itself. So assume tau is compact. Structure. So then we know that tau plus tau is also compact. Now in G plus G. And it's easy to see that tau plus tau commutes with sigma. And this is simply a direct computation, because in both cases, what you're doing simply is interchanging X and Y, if I know correctly. So let's just compute. So, intermediate composition. And we compute this. It's tau of xy is simply equal to sigma of tau x. This is all equal to tau squared y squared x. So this is simply y x. So we're simply interchanging the two factors. So remember that if we want to Cartan decomposition, we have to now restrict this map to the fixed point set of sigma and see which are the corresponding eigenspaces. Now, so GR is realized as the fixed point set of sigma, and this is precisely the graph of the compact real structure. Again, this is something that we already saw in chapter 2. And we simply have to apply theta to an element of this formula. So let's be given. Then theta x is going to be equal to x tau x, okay, and on the x is equal to x tau x. And this is precisely x being equal to tau x. So x must be in the fixed point set of tau, which I'm going to call U. So this is the compact real form of G we are considering. Okay. And now, theta of x tau x is equal to minus x minus tau x, if and only if tau x is equal to minus x minus tau x. And it's precisely being that tau x is matrix. And remember that x is in the -1 eigenspace of tau if and only if it's in I times u. So we conclude that x must be in I times u. Okay. So what this gives us is that the Cartan decomposition of the complex semisimple algebra G is going to be GR equals U plus I, where U is any compact real form of the complex semisimple algebra. By the way, it's starting to get a little dim here. So can you see the blackboard all right?
Yeah, it's perfect.
Okay, perfect. Okay, so this is enough for the examples right now.
Yeah, so basically, in other words, what you've just computed is that if G is complex, then compact real structures in it are the same as Cartan involutions on its realification. Yeah.
Precisely.
Cool.
Just our interpretation, but seeing G as a real semisimple algebra. But yeah.
Yeah.
And it also makes sense because we already know that compact real forms are conjugate. So
Yeah.
okay. So now we're going to start studying the properties of the real semisimple algebra D0 endowed with the inner product that is given from the Cartan decomposition. So first we're going to derive some elementary properties, and then we're going to state and prove a sort of polar decomposition theorem for automorphisms, which is essentially a multiplicative Cartan decomposition for the.
Can you leave the right? Wait, can you leave this board?
What?
Can you leave the right board? I'm still
sure.
making it. Thank you.
So now the D0. D0 is going to be our real semisimple D algebra with a Cartan involution theta, and we're going to give it an inner product, which Onishchik denotes by parentheses. I'm going to use angled brackets because I think it's less confusing for me. So an inner product that's going to be 0, going to be 0. And it's defined as the scalar product of x and y to be minus the killing form of x equals. So there's nothing to prove about this being an inner product, it's just the definition of Cartan decomposition. Okay. So we can talk about symmetric maps, or self-adjoint maps, and we can talk about the adjoint operator of any linear operator. So the first thing that we're going to do is to compute the adjoint of, on the one hand, automorphisms of D0, and on the other hand, inner derivations of D0. So this is given as a proposition in Onishchik. So proposition first. First, if alpha is an automorphism of D0, then the adjoint of alpha, which I denote by alpha star, is going to be the conjugation of the inverse of alpha by theta. In particular, note that if we take alpha to be theta, then it follows that theta is self-adjoint. It's an isometry, in fact. And second, If we take an inner derivation, then it must be the adjoint image of an element of G0. So I can write this in the following way. So if X is an element of G0, then the adjoint of at X is minus at theta. Okay, so let's go. And the proof of these two equalities is simply using the definition of the adjoint map. So in the first case, simply take any two vectors in V0, then take the inner product of alpha y with z, and this by definition is minus the Killing form evaluated at alpha y and theta z. But what we're going to use now is that the Killing form is invariant under automorphisms. So what we can do is we can take this alpha and take it here as an alpha minus 1, which is essentially the same as applying alpha minus 1 to the whole thing. So this is equal to minus b of 1 alpha minus 1 theta z. So this is equivalent, since theta is an involution, to minus b of y theta alpha minus 1 theta z. And now we recognize this expression again as an inner product of y with theta alpha minus 1 theta of z. So this proves the first assertion. Can I now erase the part on the right?
Yeah, sure.
Okay, perfect. Now suppose that we have an inner derivation and take what I said on the 0, then the inner product of fx, y, and z is minus the Killing form of fx, y, theta, z. And now what we're going to do is to use that the Killing form is also invariant under inner derivation, in the sense that these maps at x are skew symmetric. So now this is equal to the Killing form at y at x theta z. Now I can simply write the second part as the bracket x theta z. But I think it's clear that we can take this theta out because it's an involution. So we can rewrite this as b of y theta x z. I'm simply using that theta is a homomorphism of the algebras. And now we can recognize this Killing form as the inner product y with theta x z, except for the fact that we have plus instead of minus sign. So this is now equal to minus the angle bracket of y and theta x. It's the same y with minus theta x. And this is and the direct consequence that we get from this equality is that the elements of K are invariant by theta. So in particular, their adjoint images are going to be skew symmetric maps. And in the case that X is an element of P, then theta X is minus X. So the adjoint image of X is going to be a symmetric endomorphism. Start the basic here. So now we're going to start taking steps in order to prove Cartan decomposition for the automorphism group. So first, Onishchik discusses a bit the firstly the fact that the matrix exponential of symmetric matrices is a diffeomorphism, and then he uses this in order to prove the polar decomposition. So usually this fact that the exponential map is a diffeomorphism is pretty well known, but I think the proof that he provides here is quite unique, so I wanted to share it with you. So let's just state how this goes. So it's a section on, let's write this as a new section. So the matrix exponential map. So for now, we're going to forget about the algebras and just think about Euclidean vector spaces. So suppose that E is a finite dimensional inner product space. And I'm going to denote the inner product by the angle bracketing. So we can now consider orthogonal maps, we can consider symmetric maps, and we can consider symmetric maps. So we're going to define firstly the set S of E to be the set of symmetric maps. So the P take E to E, such that P is symmetric. And we now define P of G, P of E, sorry, to be the set of maps which are symmetric and positive definite. Okay, so it's clear that this is a vector subspace of GLE, the Lie algebra GLE. So in particular, it's a smooth manifold. And P of E is also a smooth manifold because it's an open subset of SP. So both are manifolds, and P of E is contained in S of E, and they are also related by the exponential map in the following way. So we're going to consider the exponential map restricted to symmetric matrices, then it's a standard fact of linear algebra that this map is a set bijection, basically an eigenvalue problem. And it's also clear that it's a smooth map because it's the restriction of a smooth map to a submanifold. But what's a little bit harder to find in literature is the fact that this in reality is a diffeomorphism. So Onishchik provides this very elegant proof. So he states this as a lemma. Diffeomorphism. In fact, it's an analytic diffeomorphism. So the proof is very simple. These two manifolds have the same dimension because P of E is open in S of E. So the only thing that we have to do is to check that the differential is non-singular. So let take any symmetric matrix x in s of p. And we only need to prove that the differentials of the exponential map at x, which goes from the tangent space of S of p, which is S of p, to the tangent space of P of p, which is S of p again, that this is non-singular. Okay. Suppose not. So then we can find a direction in which this differential vanishes. Suppose not. So it exists symmetric isomorphism in Y such that 0 is the differential of the exponential map at x in the direction of y. So note that the tangent vector y is determined by the straight line going through x with direction y. So this differential can be reinterpreted as the derivative at time 0 of e to the x plus t y. Just 1 second, I'm going to turn the lights on. Okay, much better. So it's a standard fact of the matrix exponential map that if you have any square matrix A, that A and its matrix exponential commute. So we're going to simply apply this fact to this straight line generated by x over y. So e to the x plus 3y multiplied by x plus 3y is equal to x plus 3y times e to the x plus 3y. So simply take the derivative of this expression at time 0 and you get that. This derivative is simply the differential of x at y. So this part is times this at 0, which is simply x, plus this at 0, which is e to the x, times y. This must be equal to y times e to the x plus x times the derivative of the exponential map x in the direction of y. So these two terms are going to vanish. And what this means is that e to the x at y is also equal to e times y to the x. So y commutes with the exponential of x. So in particular, we could take a basis of common eigenvectors, and those matrices which appear in the matrix representation with respect to that basis are going to commute. So from this, what you get is that in reality, not only do these two matrices commute, but x and y have to commute. Please. X and y. This implies that xy is equal to yx. And now, for commuting matrices, we know that the exponential of a sum is the product of the exponentials. So we can simply go back to this first equality. We obtain that 0 is equal to the derivative at time 0 of this product of exponentials, e to the x times e to the x y. And this is simply e to the x times y. And now simply use that e to the x is a linear isomorphism to deduce that y is equal to 0. Okay. So this proves the non-singularity of the differential, because the matrix exponential is a different constant. Okay. Now we're going to call the inverse of this map the logarithm of a positive definite matrix. So let's start right from here. Define, I call it log, to be the inverse of the exponential map from positive definite matrices to the matrix. And we're going to use now this map in order to prove the polar decomposition, the classical polar decomposition theorem for linear isomorphisms. I'm just going to erase here. The maps. This is the map that takes orthogonal operators and positive definite operators and simply multiplies them, then this gives us a linear isomorphism. Or alternatively, we can think of the map that goes from OP times SE to GLE stays K to K. K and x to K times the exponential of x. And both these maps are also smooth diffeomorphisms in the space. In particular, every isomorphism factors as the product of a rotation and a positive definite map. And again, the proof of this theorem is quite simple. To first note that the only difference between the first map and the second map is that you can go from the second to the first by simply taking the exponential map. And the exponential map, we already know it's a diffeomorphism. So the moment that we prove that any of these two maps is a smooth diffeomorphism, we already do it. So I'm just going to focus on the second case. Okay. So for the proof, since A and B differ by the exponential map, we can just prove So what I'm going to do is to simply write down the inverse map of this and to check that it's smooth. So I think I'm going to give this a name. Let's say this is phi that goes from SE to GLE. Phi of K X squared minus 3x. So let's take any linear isomorphism and try to find a K and X for which this expression gives us our original isomorphism. So let A be given. And we simply solve the equation K A to the X equals A. K and X are in OER as irrespectively. Okay. Suppose that we already have the decomposition. So if A is equal to K times e to the X, then we can take the adjoint of A. So we can take the adjoint of A and then put simply the product of the adjoints with the order reversed. The exponential image of a self-adjoint map is self-adjoint. So e to the X adjoint is e to the X. And the adjoint is K is its own inverse. It's K to the minus 1. So if we multiply this by this, we can get rid of both K's. It's going to be equal to e to the X to the X. And this is simply e to the 2x. Now, it's a standard fact that if A is a linear isomorphism, then this product is a positive definite self-adjoint map. So this can be thought of so we can simply take the logarithm of this and it should be equal to 2x. Okay. So A star A to x is equal to log of A star and then x is equal to 1/2 log A star A. So now we have x, and if we want k, the only thing that we have to do is to simply solve this equation. So k is simply a to the a times a times e to the minus x. So this should be a to the e minus x this correctly, I think so. Yeah. So we have solved for x and k. Note that these solutions are unique. So what this means is that in reality, this is precisely the inverse map of the map B given here. It has inverse of A equal to A means the exponential of minus 1/2. Well, one could simplify this and simply say that it's the square root of A star A, but the inverse of that. And x is going to be equal to 1/2 log A star. And now clearly this is a smooth map because everything involved here is smooth. So
should it be phi inverse of A?
Sorry?
Should it be phi inverse of A?
Yeah, sure. Thanks, Simon. So yeah, phi minus 1 is smooth. So this means that phi is a diffeomorphism. And thus B is proved, and so A is proved. So I think I can go on for about 10 more minutes. Right. So now Onishchik goes directly to the proof for the automorphism group. But I'm going to take a very small detour from what Onishchik does, and I'm going to derive the Cartan decomposition from the properties of what are called algebraic subgroups. This is essentially the same that what Onishchik does, but simply under a new branding. So the main idea is that we can regard being in the automorphism group as being the solution set of a system of polynomial equations. So the automorphism group is an algebraic subgroup, and algebraic subgroups of GL and R have some special properties that make the polar decomposition work for not only the automorphism group, but any algebraic subgroup. It's a little bit of a stronger theorem that we basically will prove with the same methods that Onishchik uses. But yeah, just beware that I'm going to take a very small round trip. So just write this as a sort of aside. I think I've run out of chalk now. So let's suppose that we have a matrix group be any subgroups. Then we say that G is algebraic if it's given by a system of polynomial equations. It's the set of all matrices that satisfy a set of polynomial relations. We are using the coefficients of A. So now it's pretty easy to see that these subgroups are closed because they're defined by a system of equations, continuous maps. So it's a closed subgroup, it's a subgroup by the Cartan theorem. And so we can consider the exponential map restricted to this. Just before this, I'm simply going to make it clear that the automorphism group is indeed algebraic. Let's see. Zero is to the algebra. Zero is algebraic. This is simply because the condition of being an automorphism can be simply seen as preserved in the bracket. For every pair of vectors. And this can be regarded as a system of polynomial equations. Okay. Now, the key fact that I'm going to need from this group being algebraic is that, in general, if you have an element, you have a matrix subgroup or something of the sort, and you take any element of GLNR of the Lie algebra of GLNR whose exponential is in the group, that doesn't mean that this element is in the Lie algebra. So if, say, if e to the x is in a certain subgroup G, this does not mean that x is in the Lie algebra, because being in the Lie algebra is not only this, but e to the tx being in G for every t. But we're going to give a sufficient condition in which this implication is true. And this is going to be the key fact for automorphisms. And after that, I'll stop. So I'll write this as a lemma. G is algebraic. And X is an element of GLNR. Such that first, X is diagonalizable. And second, e to the x is in G. Then X is in the algebra of G. So we need this property, being diagonalizable, in order for these two conditions to be equal for algebraic subgroups. So the proof is not so complicated. So first, any conjugate of an algebraic subgroup is again algebraic because conjugation is essentially a polynomial map. So we may already assume that X is diagonal. So since conjugates of algebraic subgroups algebraic we may assume X is a diagonal matrix. So it's a diagonal matrix that satisfies all the defining polynomial equations of G. Okay. So we want to see that not only the exponential of x satisfies this, but the exponential of any multiple of x satisfies this. Note that since e to the x is in G, and G is a subgroup, then e to the tx is also in G whenever T is an integer. Now, let f be a defining polynomial. G. So one of the equations that appear in the system that defines G. And
it was a little tough to write this, but
so we know that f of x is equal to 0, and f of tx is also equal to 0 whenever t is an integer. So essentially, since the exponential of x of tx is the diagonal matrix with coefficients e to the txi, since e to the tx is the diagonal then when we write the f at e to the tx, this is going to be a polynomial in these exponentials. So essentially, you can gather terms in order to simply write this polynomial in another form, in another fashion, which is the following. So then write f of t e to the tx as a sum lambda k e to the t equals for k goes from 1 to a certain degree. I don't think I don't know if this is clear enough. Essentially, I don't want to go too deep into this, but essentially we're simply taking the polynomials, we're using the fact that the exponential of a sum is the product of exponentials, and we're using the other terms in this way. I don't know if this is clear enough.
Wait, can, above you have f of x is 0. Shouldn't that's what we know? Because like we know that f of e of x should be 0.
Yes, f of e of x is
Okay, that's better. Yeah, can you repeat what you were saying now then? I was kind of confused by that.
Okay, so when you apply f to this diagonal matrix, then this is a polynomial in e to the tx1 up to e to the txn. So it's going to involve monomials, which are e to the t to xn plus. It's a polynomial in. So say, for example, that you have a polynomial that has e to the t1 and e to the tx3 squared. Then you can write it as e to the t x1 plus 2x3 and so on. So essentially, you gather terms in this way in order to see this polynomial as another polynomial, but in e to the t times some coefficients, which essentially involves these sums, integer sums of coefficients. I don't know if this is. So we have this polynomial function, polynomial exponential function that vanishes on the integers, and we need to see that it vanishes in the real line. So for example, let's order these coefficients, assuming that the n is larger than the n minus 1, and so on. We can do this, and we assume that the first coefficient lambda n is not 0, so this is the highest coefficient in a sense. So if f of e to the tx is not everywhere 0, then there is a non-zero coefficient with which, and we can simply take the one of highest order, which should be lambda n. Lambda n is not equal to 0. And now, once we do this, we're simply going to divide by this associated exponential. So e to the minus t the n f to the e to its legs is equal to first the term of highest order, which is going to be lambda n, plus a sum of lesser order terms, which are on the form lambda k, with e to the t dk minus dn. We're assuming that this dn is the maximum exponent, so this is negative. And now when we take t to infinity, this means you're close to zero. To lambda n plus zero. But now this is a contradiction because this function should vanish in the integers. Contradiction. And now this finishes the proof, because we can apply the same reasoning to every defining polynomial, and we conclude that e to the tx is in G for every t, and thus x is in the answer. So I think that's everything that I wanted to talk about for this session, and in the next lecture we'll see how we can use this lemma in order to prove the polar decomposition for algebraic subgroups, and how to quickly derive it for the case of the automorphism group.